Hello everyone. So the next type of problem on displacement method or the flexibility uh, matrix method, that is the stiffness matrix method, is analyze the continuous beam as shown in the figure. If the B support sinks by 10 mm, use displacement method, take EI is equal to 6000 kilonewton meter square. Okay, so in this type of problem, the different thing about this problem is, in this they'll ask you to find out, they have asked you to find out the displacement using the displacement method, analyze the continuous beam. If the support B is sinking, now it is like a sinking support problem. So B is sinking by 10 mm. Okay, so first as usual draw this diagram. A and D are fixed and B, C has a roller support, and again you can notice the I values are different throughout the beam, but there is no external loading at all in any beam, any span A, B, B, C or C, D. Okay, there are no external loads. So but only the loads, there is a sinking of the support B is happening. Okay, and that too it is by 10 mm. Okay, so first draw this, then first find out the Ki. Now I'll tell you how to find out this Ki. This Ki, this formula will not hold good when both the ends, both the ends are uh, the last supports having, if they're having a fixed support, then this formula will not hold good. Anyhow, we'll just check. Okay, how to find out this. So Ki is equal to 3j minus r plus m. So joints are 1, 2, 3 and 4. So 3 into 4. Reactions, okay, fixed support 1, 2, 3, 4, 5, 6, 7, 8. 8 reactions plus members 1, 2 and 3. So it is 12 minus 11. So kinematic indeterminacy is 1. But according to the concept, what we know, that is, see here, fixed support in this, the reactions, it will not allow the joint to move anywhere. Similarly in D, it will absolutely not allow the joint to move anywhere. Okay, so the only thing what moves here is, these are the roller supports. The reaction is, that is vertical reaction, is stopped, but still it can move in the second direction, and the second direction happens to be a rotation as such here. It happens to be a rotation, that is in coordinate direction 1 and coordinate direction 2. Okay, and so next is, once you find out this coordinate directions here, next mark this, that is here, but Ki is equal to 2. According to the formula, it is 1. But when both the ends supports are fixed, it will not hold good. This will not, you cannot find out. So we have to use the concept that in that case. So we have to use here, so Ki is equal to 2, because you have to, this is a roller support, it can rotate only in these two different directions. Okay, all right, once you find out this, next is draw the diagram wherein the support is sinking. Now you can see here A is fixed, B is sinking. So B is sinking, that means it should be show here, it is 10 mm, and then again it comes back to C, and CD is straight. Okay, all right, so next is find out the fixed end moments. And to find out the fixed end moments, here there are no loads acting here. No, the, so what used to do is, first whenever we're finding the fixed end moments, used to write the formula for the load conditions. Once you find out the formula for the load conditions, later used to find out the given problem which to apply. Later used to add one more formula, that is 6 EI delta by L square. That is nothing but, now the 6 EI delta is nothing but, see, if you multiply the previous formula, 2EI by L in plus 3 delta by L. Okay, we had written here 2EI. So always used to write the formula for slope deflection equation is 2EI by L, then open the bracket, then theta A plus 2 times theta B, plus last factor would be minus 3 delta by L. Okay, so the last term, that is 3 delta by L, that 3 delta by L should be multiplied with 2 EI by L. So 2 EI into 3 delta. So it is 6 EI delta divided by L into L is L square. That is the same. When you split them, it becomes 2 EI by L, open the bracket, 3 delta by L. So when you multiply both, it becomes minus 6 EI delta by L square. It is the same formula which we have used. Okay, all right, so it is the, now you can see here A, right side support is with respect to AB, again right side support is sinking, so right side support is sinking, so it is minus 6ei delta by L square. So it is 6ei, okay, that is 2i. First use the formula here, delta again, keep it in terms of meter, because on the given problem everything is in terms of meter. So mm convert into meter divided by L square. Okay, so it is minus 6 ei, already we know the formula. So ei formula is 6000 into 2 into I. Okay, so ei together 6000, 2 into 0 0.101 divided by L square. Okay, so mfab is minus 80. Okay, next similarly mfba is also same. This support is sinking, so it is minus 80. Similarly, come down to next bc. So bc is, so again with respect to this joint, okay, support in bc, right side support is constant, left side support is sinking. So left side support is sinking means it is plus, so it is plus 6 ei delta by L square. Okay, so it is this, so it is plus 56.25, this is plus 56.25. Okay, now p value. So the value of p is, there are no external loads acting, and obviously there are no movements also acting anywhere here in the original diagram. So obviously these two coordinate direction will be 0, that is at b and c. Next pl. Okay, find out pl, and this for first load. MFBA plus MFBC is first term. Next MFCD, whichever this thing is bending, no, only that will take. That is MFCD is equal to 0. All right. See here, MFBA, MFBC. Add these. Then MFCB is this, which we have already calculated. So PL is equal to, in both the direction, that is minus 23 plus 56. Okay, so once you find out this P and PL, next is find out the stiffness matrix. Now to find out the stiffness matrix, it is you apply your unit displacement in coordinate direction 1. So so it's the coordinate direction 1. Fix all the support, only release joint B. That is coordinate direction 1. In coordinate direction 1, you apply unit displacement in coordinate direction 1. That is theta B is equal to 1. So again, it pushes, whenever this beam bends, it pushes BC downward, and it in upward direction pushes AB. All right. So it is like this. So mark this deflected shape of the beam. Then mark this rotation. So see here, only in the coordinate direction 1 and 2 you have to mark this K1 and K2. So first write K1 and this is K2. Right. Now you are applying the load or applying the rotations at 1, that is in first coordinate direction. So it is K11. Here also you are applying rotation in the first direction. So it is K11. Okay, so here it is K11, here it is K21. Second direction K2, K1. Then you're applying rotation at 1, that's why 1 and 1. Okay, so once you mark this, next is K11. So K11 is nothing but, it is connected to, see here it is pushing left side also, right side also. So it is MFBA plus MFBC. Okay, then use the formula MFBA. So it is 2EI by L, then 2 times theta B plus theta A. Then right side plus 2EI, that is 2.5. Again here I value is different, check out that. So 2 times theta B plus theta C. See, only theta A and theta C would be 0 because they are all fixed. Only wherever you apply the rotation, that particular joint would have, you have to release that particular joint. Okay, all right. So once you solve this, then you'll get K11, that is 5.167 EI. So again, if you get in fractions, simplify that and keep it in decimals, because ultimately we are using the decimals and we are putting it in the matrix form. Okay, and next similarly K21. So K21 is left side, MFCB. So MFCB is equal to 2EI by L. Then CB, so it is 2 times theta C plus theta B. Theta C is 0. Okay, then so it is 1.25 times EI. All right. Theta B is nothing but 1. Okay, so we'll get this. Next, second one, apply unit displacement in coordinate direction 2 now. Okay, so coordinate direction 2 is this thing now, 2 direction. All right, so this would be theta C is equal to 1 radian. So 1 radian means it tries to push CD downward. Because it tries to push CD downward, it pushes BC upward. Okay, once you mark this, then K1 Okay, this is coordinate direction 1. K1, K2. First direction is K1, K2. Then you are applying the rotation, that is theta C is equal to 1 in second direction, second coordinate direction. So that's why you have to put this as 2 and 2. Okay, once you put this 2 and 2, so now you get K12, K22. So now find out K12. Okay, so K12 is, okay, just check which is bending here, K12. So it is MFBC. So it is MFBC, that is 2EI, 2.5I into 2 times theta B plus theta C. Okay, next find K22. So K22, okay, so it is both this are bending. It is MFCB plus MFCD. Okay, so MFCB is 2EI by L, 2 times theta C plus theta B. Okay, then again same CD, it is 2EI by L, 2 times theta C plus theta D. Okay, so theta D is 0, theta B is 0. Okay, then apply to theta C is 1. So you'll get 2.5 plus 2.5, that is K22 is equal to 5 EI. Okay, so once you solve this, next is stiffness matrix. So stiffness matrix is given by the equation K into delta is equal to P minus PL. Okay, so K into delta is equal to P minus PL, that is K11, K12. So write this first row K11. No, I've written here differently. No, this is, you have to write it like this. K1, K1 means first row, first column. So this is K21, you have to write it as, okay, but anyhow, both will be same only, 1.5, 1.5. K21, okay, here K12, that means first row, first column, first row, second column. Here also K21 it is, second row, first column, this second row, second column. Then into delta 1 into delta 2, delta 1, delta 2 is equal to, then P minus PL, P minus PL, put the formula or whatever you have calculated before, just substitute. Okay, so now it is uses formula EI, take it common. So 5.17, 1.25, 1.25, 5. Delta 1 into delta 2. Then minus this. Okay, write this here. So delta 1 into delta 2, 1 by I goes here. So this will become inverse. So 5.17. So this matrix goes inverse. Okay, into this. So this would be 1 over EI. 1 over, again I've used I've done it manually here. You all please don't do it manually because it become very hectic. So it's always a better way to do it in the calci. So again it is simple, 2 by 2 matrix. Again whatever previous steps you have calculated, the same how use it in the calci. This is mat A inverse, mat B. So when you solve it in the calci, so you get theta B. So theta B is equal to 7.758 over EI. Theta C is minus 13.18. Okay, so it's minus 13.18. So put it back in the equation. So MAB is equal to fixed end moments. Okay, so it's a fixed end moments plus 2EI by L, then 2 times theta A plus theta B. So all this, you have theta B, you've got the value, substitute here. Next, similarly, MBA. MBA is again fixed end moments plus 2EI by L, 2 times theta B plus theta A. Put it back in the equation. Then MBC, fixed end moments plus, here it exists both, 2 times theta B plus theta C. So put both the values here and solve. So the check should be, this should be equal and opposite. They're almost equal and opposite. Okay, then finally MCB is fixed end moments 2EI theta B plus theta C. Okay, we have solved only up to BC, BC, that is CB. And CD will not solve because in CD there are no loads only. There is no loads, there is no bending happening here. So no need to find MFCD, MF and MFDC. Okay, so once you calculate all the moments, sum up all the moments, just check whether this BA and BC are equal and opposite. So if they're equal and opposites, so what you have done is right. Okay, all right, so with this we end up with the sinking of the support. So in the sinking of the support, just be careful, first draw all these diagrams one by one, and then, because in this case it's a simple problem because there are absolutely no external loads acting. In case if the external loads acting, you have to consider the external loads followed by this factor, that is minus 6 EI delta plus 6 EI delta, both you have to add in case if you're considering the external loads. Okay. All right, that's all for today. Thank you.